Welcome back to A Slice of Physics. Having reviewed the concepts around projectile motion in the previous video, it's now time to take an example. We're going to look at a ball that's tossed horizontally and determine things like the time it spends in flight, the range of its motion, and the speed of impact with the ground. Here's the question we're looking to tackle today. It says that Jerry holds a basketball over his head and tosses it perfectly horizontally with a speed of 5.0 meters. I know the speed, I know the direction, so I know the velocity. The ball is 2.5 meters above the ground when it leaves his hands. And then it's asking how long is the ball in flight before it hits the ground, how far ahead of him does it hit the floor, and with what speed does it hit the ground. You know I've been emphasizing process all along, so here are the process steps that we need to follow to solve a problem like this. We always start with drawing a picture that captures all the information. We set up our coordinate axes, understand what's given and what's being asked for, and then solve based on that. So let's start with a figure here. Again, we don't care so much about the artistic value of the picture, but we do want to capture all of the information that we need to solve the problem. So here's the basketball that's being tossed with an initial velocity. We know VI is perfectly horizontal of 5.0 meters per second. We also know that it is at a height of 2.5 meters above the ground at the moment it's tossed. And once it leaves Jerry's hand, it's going to do a projectile motion and hit the ground somewhere over here. And what's being asked for is this: how far ahead of him does it hit the ground? We're also being asked for delta t, how long is it in flight? And thirdly, we're being asked for the speed of the ball at this moment of impact. Okay, having captured all the given and asked for information in the picture, we've done step 1. The next step is step 2, which is coordinate axes for projectile motions. We said that the typical coordinate axes of x positive to the right and y positive to the top is common, so we will choose that. We've kind of discussed this step 3 along the way, but now let's list the specifics. As mentioned in the last video, we can solve projectile motions independently along the x and y axes. So let's start setting up what we have for the x-axis and what we have for the y-axis and see where that leads us. So for x, I've got VIX is 5.0 meters per second, and I can put a positive sign next to it just to confirm that it is along the positive x-axis. I know that AX is 0. Remember, whenever we have projectile motion, there is no acceleration along the horizontal axis. It's all vertical. So now adding my equations of motion here and remembering that AX is 0, this third equation here becomes delta x equals VIX times delta t. The second term, A is 0, so the second term goes away. That's a simple equation. I know VI, but the problem is I don't know delta t, so I can't get delta x yet. And there's nothing much more I can do with the x direction. So I'm kind of stuck for right now, but I do remember that I got another direction I can work with, so let me move on and see what that does for me. So for the y-axis, here's all the things I have. Do I know my VIY? What is the component of the initial velocity along the y direction? Well, the initial velocity is all along horizontal, and anything that's all along horizontal has no component along the vertical, so VIY is simply 0. If you look at just the y-axis, there is no initial velocity. AY is minus 9.80 meters per second squared because this ball is falling under the acceleration due to gravity that points straight down, and that's its value. And I also have something else in the y direction. I have the total displacement. So delta y is 2.5 meters, but I got to be careful. It's a negative 2.5 meters because it's moving in the downward direction. Final position minus initial position will be a negative value. So that's what I have. And now I can look at this third equation here and write it in the form that we need to use it here. Delta y equals VIY times delta t plus 1/2 AY times delta t squared. Now because VIY is 0, the first term goes away. I know delta y, so let me start putting in the values. I got minus 2.5 meters equals, this whole first term is 0, plus 1/2 times negative 9.8 times delta t squared. I'll let you do the algebra, rearrange it, and solve it, but when you do that, you will get delta t is 0.71 seconds, down to 2 significant digits. So we already solved one of these questions. We know how long the ball will be in the air before it hits the ground. Now, even though we said x and y motions are independent, there is one thing that ties them together, and that's the fact that the time that the ball spends in flight is the same for the x motion and the y motion. The ball's not moving horizontally any longer than it is moving vertically. So once we get this delta t, we can use that over here. And by the way, that's why we don't call this delta ty and delta tx. They're always the same, so we just call them delta t. So now I can use this delta t to get my delta x, which is plus 5.0 meters per second times 0.71 seconds. The seconds cancel, and this ends up being 3.6 meters. Positive value means that it's going along the positive x-axis, which makes sense. It's going to the right. So we've solved a second question. We now know how far ahead of him it hits the ground. The third question we're left with is to determine the final speed of impact. We know that speed is nothing but velocity without a direction. So let's look at the final velocity. What do we know about it? Well, we know its x component. Because the x-axis is a uniform motion with zero acceleration, the final velocity is the same as the initial velocity. So here's my vfx, and that's also 5.0 meters per second. There is also a vfy. I don't know what that is yet, but if I get that, I will have both the components of the final velocity, which is helpful in my determining the final velocity's magnitude and direction, and the magnitude will be the speed. So back to the y direction. I've got all this now. Can I figure out the vfy? I've got my choice of equations now. I can use several, but let me just use the second equation over here and say vfy equals viy plus ay times delta t. I know my viy is 0. I know ay is minus 9.8, and I know delta t now is 0.71. And when you solve that, you will get minus 7.0 meters per second. So the vertical component of the ball's velocity is going to be minus 7.0 meters per second. The horizontal component remains unchanged at plus 5.0. So let me show those two components over here. I've got the x component as plus 5.0. I got the y component as minus 7.0. And we want to determine the sum of those two components. The sum of components of the vector gives you the final vector. So if I slide Vy over here, my final velocity will be this hypotenuse from the original tail to the final tip. So this is my Vf. The length of that arrow is the magnitude. This angle here will be the direction. They didn't ask us for the direction, so I'm not going to solve for that. But to solve for the magnitude here, now I got a right triangle. I want the hypotenuse. I know the legs. So Vf squared simply is Vfx squared plus Vfy squared. So this gives me for Vf square root of 5.0 squared plus 7.0 squared. And that is 8.6 meters per second. So that's my final speed. If the question had asked for the angle of impact with the ground, we can easily figure that out from this right triangle using our SOHCAHTOA. So to recap, it didn't look like this problem gave us much information. It only gave us 2 things and asked for 3 things. That seemed to be an unfair bargain. But when we set it up and go through the steps, we solve the problem to obtain all 3 unknowns. We know that it's going to spend about 0.71 seconds in the air. It doesn't take that long to fall to the ground. It goes 3.6 meters ahead of him before it hits the ground, and it hits the ground with a speed of 8.6 meters per second. In this slice of physics, we got some good practice solving a projectile motion example by taking each axis independently and solving for the unknowns. Thanks for watching.